Hello. All right, so we're continuing on with vectors. So we're going to wrap up chapter 3 today. We're skipping a couple sections at the end of chapter 3 about multiplying vectors. We will actually need those sections in this course, but rather than introduce them now and never talk about them for like 5 more chapters, we will come back to those sections in the book once we are closer to needing them. But before, let's see, so if we go back to the last lecture, we saw how we could define vectors as something that has both a length or a magnitude and a direction. So we signify that by an arrow to represent the path, and the length of the arrow might represent something about its magnitude. So this might be something like a vector g that is pointing straight down. And we saw how we could multiply vectors by scalars or by constants. So this might be, say, 2g. A vector that is twice as long as g. Where something like this might be something that's more like a negative 1/2 g. The scalar just rescales the scalar, and with the if there's a negative sign out front, that flips the direction that the vector is pointing in. So the notation was that you had some general vector r with a little arrowhead above it to signify that it's a vector, where I like the absolute value notation to represent that this is the magnitude of r, or the length of that vector. To further review, we also learned how to add vectors together. Geometrically, adding vectors together is nothing more than drawing out the first vector. So if I use the 2 examples I've already written on the page, that might represent r. And then at the tip of r, I then place the base of the next vector g. So then I might draw g to go down like this. And the resulting vector goes from the start of everything to the end of everything. So this would represent r plus g, for example. In this case, it looks like overall that vector just points in the horizontal direction to the right by following those 2 vectors. Even though r itself went to the right and up, but then g went back down, ultimately your net displacement, if this were a displacement, for example, would be to the right. Similarly, r minus g, again, for all, you do the same thing, but instead of adding to it g, you could think of this as adding to r negative g. So negative g is just g, but it points in the opposite direction. So this would be negative g, this is r. As a result, the answer of r minus g might look something like that. It is pointing both to the right and upward in this case. All right, but now we want to be more quantitative about this. We also want to be able to say something about what these vectors represent inside some given coordinate system. So before, we have been laying down coordinate systems where for 1D motion we've defining a positive direction and a negative direction. That was in essence us defining our coordinate system. Here we're going to extend this to now allow for multiple dimensions, so 2 dimensions. So a coordinate system, for example, might look something like this. This might be an example of a coordinate system. Perhaps this is an x-axis and this is a y-axis, like you've seen in math. But we can think again about what I'm saying when I draw something down like this. I again am specifying that there is an origin. And these arrows here are specifying that there is a positive direction for both the x and the y directions. Really what you have here is you have two 1D coordinate systems. You have a 1D coordinate system in the horizontal direction, then you have a 1D coordinate system in the vertical direction. And those are being laid on top of one another to define a 2D coordinate system. So I could specify my location not just where I am along the x direction, but I could also specify where I am, say, in the y direction. And the positive and the negative values, again, just corresponds to, in this reference frame, in this coordinate system, whether we are moving, how we are placed, say, relative to the origin. So these sorts of coordinate systems, again, probably the only coordinate systems you've ever seen, where you have essentially two lines that are perpendicular to one another. So this is what is called an orthogonal coordinate system. Orthogonal is just a fancy word for perpendicular. The two axes in this case, this might be x and y again, for example. All it means to be orthogonal is that those two axes are perpendicular to one another. They make a 90-degree angle with one another. And in this class, we will always be working with orthogonal coordinate systems. You might think, is there any other? I could define, for example, this could be a coordinate system where maybe this is, I'll call it the A direction, and this is the B direction. In that case, I could define my location by specifying a location on A and a location on B, and that would define my kind of location in this 2D plane. But it's a little bit more complicated to deal with compared to if we just stick with orthogonal systems. So I'll give that a big X. That we will not be dealing with that in this course. We will stick with orthogonal systems. Indeed, it will actually be imperative that we are using orthogonal coordinate systems when we do things like the dot product and the cross product and talk about motion in multiple dimensions. By allowing things to be orthogonal or perpendicular to one another, it actually allows us the benefit that we can treat each dimension independently of one another. What goes on in the x direction does not influence what is going on in the y direction, for example. That will probably be, if not the next lecture, the lecture after that. All right, suppose you have some 2D coordinate system, then again, I can draw vectors within that coordinate system. This might represent some vector r. Maybe this represents some vector g, for example. Those are vectors that we are now drawing, but on top of a coordinate system, where the coordinate system has tick marks, has an origin, has directionality. It allows us to now get a little bit more quantitative with what is going on with these two particular vectors. So, how do we do that? To state, for example, these vectors r and g in this coordinate system, we can resolve the vectors into components. And what is a component? A component for each dimension we're considering, each dimension. So in this case of 2D, there are going to be two coordinates that we have to specify for every vector. In a 3D coordinate system, where there's maybe x, y, and z, we would have to specify 3 numbers. And what each of those numbers are saying is essentially saying what the vector is doing in each of those particular directions. In the two cases I've drawn, both g and r appear to be pointing somewhat to the right. So there is a horizontal component to those two vectors. Excuse me. And that component we expect following this coordinate system should be positive because the positive direction is to the right for the x direction. Whereas the vector r is pointing slightly up and the vector g is pointing slightly down, so we would expect they also have vertical components, but the r vertical component will be positive and the g vertical component will be negative. Because if we just look at the y direction, whether it's up or down, r is pointing slightly up and g is pointing slightly down. You could contrast that with, say, a third vector, h, which maybe h looks just like this. In that case, it's entirely vertical. There is no left or right component in that case, so there's no horizontal component for h, or rather the horizontal component is 0. There is no direction, there's no pointing at all in either the left or the right direction. There's only pointing in this case, up. So there's a y component, which in that case will be positive. So there's a couple different notations that are used, and I will likely alternate between most of them. So let me write down for some vector r. Well, I guess I've already used the letter r above, so I'll say for some general vector s. Yeah. You can write the components as either something kind of in brackets, where there might be s comma x and x comma y. Where again, this first number, which is just going to be a number like 1 meter or -6 meters per second, that is saying what is going on in the x direction. Where this is telling you what is going on in the y direction. So if that first number is positive, that says that the vector itself points to the right in some way. And if the second value, s sub y, if that number is, say, negative, that means that the vector also points downward in some way. And then the combination of the two gives the direction that the vector points in 2 dimensions. Another way you might see this written is as a column. So you might just see it written as sx, sy, like this, kind of one on top of one another. This isn't a fraction. This might be considered, a very simple column table, where the top number is the x component, the bottom number is the y component. For the engineers, there's also the ijk notation, which sometimes you'll see it written like this, where the x component has this letter I with a little chevron on top of it. So that is just the engineering notation for the x direction, and the j is engineering notation for the y direction. And then if you have a third dimension, there's also k. So k represents the z direction. So I can say, for example, that if I were to say s equals 3, 2, that's saying something about how much the vector is pointing in the x direction, in this case positive 3, and how much the vector is pointing in the y direction, in this case positive 2. So let's actually now try to think this out and think of what this means. And I'll just use s is 3, 2. So the fact that the x component is 3 means that if I have some starting point here, the length in the horizontal direction is 3. It goes 3 units to the right, for say, if right is positive. And then it goes 2 units upwards. So this has a length 2. And then the line that I draw kind of connecting these two, this corresponds to s. So the components of the vector is telling you how much it moves or how long it is in each individual direction. And you might think this kind of looks like we've added 2 vectors. It looks like we've added a horizontal vector 3, and then to that we added a vertical vector with length 2, and then s represents the vector sum of those 2 vectors. And that is essentially the motivation behind this engineering notation. So the engineering notation would say that this vector is 3i plus 2j. So you could think of this one as a completely horizontal vector that points with length 3 to the right, and then on top of that you add a completely vertical vector that points of length 2 positive upward. And the sum of those two gives S. Now what is nice is that if we're just thinking about lengths of vectors, the base has length 3, that vertical branch has length 2, and now I want to know what the length of the part I drew in red is. But you might notice a fairly familiar geometric shape has been drawn. We have our good old friend, the right triangle. Because these guys are, since they are perpendicular to one another, this is nothing more than a good old right triangle. And what's lovely about that is that allows us to actually now write down a formula for the magnitude of the vector. The magnitude, the length of the hypotenuse in this case, you can evaluate just by a simple application of the Pythagorean theorem. So in this case, it would be 3 squared plus 2 squared. All that in the square root is the length of this particular vector. So then that's square root of 9 plus 4 plus 13. So the length of this vector, we would say, has a length equal to the square root of 13. So 3 point something. Hopefully you are not completely averse to Pythagorean's theorem, because we're going to be seeing a lot. Right triangles pop up a lot in this class particularly, and in physics in general. And notice what we did here. We got the magnitude of the vector by looking at the individual components and composing it as a right triangle. So if I were to write this down as a general formula, I might have some triangle here. Here's the length of some vector r. Here's the x component, and here's the y component. In that case, I can say the magnitude of a vector is nothing more than the square root of the x component squared plus the y component squared. It's, I think, worth a highlight as the general formula for the magnitude of a vector. And again, if there's a third component, if this is a 3D vector, then it's rx squared plus ry squared plus rz squared, all in the square root. Pythagorean's theorem extends to as many dimensions as you want. So again, for example, if I tell you that I have some vector w, and I have, maybe I'll write it like this, is 3, 4. So again, what does that mean? That means in the x direction, it goes out 3, and in the y direction, it goes up 4. Going from my starting point to my ending point, that is the vector w in this particular coordinate system. And I could ask, what is the magnitude of this vector? In that case, it is just 3 squared plus 4 squared, all in the square root. This is a 3, 4, 5 triangle. You can convince yourself this evaluates to 5. So these are examples of, given the components, this tells you how to get the magnitude. Tell me how big the vector is in each dimension. I'll just do Pythagorean's theorem, and I'll tell you how long the vector is itself. Okay. Oops. Now let's look. Now let's look at, suppose I have some coordinate system. Maybe define this as the x, this is the y. and the arrows tell me which direction is the positive direction. Let's see how we can think about how we add two vectors. So again, suppose I have some vector r, which has an x component and a y component. And then I have some vector g, which has some x component and some y component. So two different vectors. Geometrically, we know how to add two vectors. I take one vector, I lay it down, then I take the next vector and I lay it, point to tip, and then I trace the starting point to the end point. So let's do that here on this axis and see what we get. So suppose this is the vector r. And then suppose on top of that I add the vector g. And I'm just kind of making these up for arbitrary two vectors. What we will write down will be true for any vector, or any set of vectors. So let's look at r first. So r, it looks like it goes to the right and also goes up. I can talk about what those components are if I kind of imagine some dashed dotted lines. This length right here is the length r sub x. That is the amount of distance the vector points in the x direction. And then this is r sub y, the distance that the vector points in the vertical direction. I can do the same thing for g. G kind of starts here, and then it ends here in the vertical direction. So this would be, say, g sub y. And then, oh dear, it's a terrible straight line. Yeah, it's just as bad. So then if I looked in the horizontal direction, this would be, say, g sub x. And then if I were to draw the sum of the two vectors, again, we've kind of just already drawn it for ourselves. This arrow that I'm drawing here in black, that would represent r plus g. But just by staring at this coordinate system, it is easy for us to then write down what the sum is. Let me call this sum s, so it's not confusing. So s, again, it starts here at the origin. If I were to drop down a line, this represents the horizontal component of s. And then if I were to have a line here, this represents the vertical component of s. And I think with a little staring, you can convince yourself that the sum in the horizontal direction is just the sum of the individual components. And the sum in the y direction is just the sum of the individual y components. And that is true in general. Give me two vectors that have components, an x component, a y component, maybe a z component, maybe even z components, maybe a fourth dimension. I don't know. And I want to add the two vectors together. I just add all the x's together, and that's my new x component. I add all the y's together, that's my new y component, etc., etc. So for example, if r equals, maybe it's the vector 2, comma 1, and then g is the vector, say, 1/2, comma -1. So if I were to sketch this, I might say, okay, r goes over 2, up 1, so maybe that's r, and g goes to the right 1/2 and then -1, so it might look something like this. That might be g. Now if I wanted to add them together, I could recopy g over at the tip of r, so that's also g. And then in this case, actually that's not drawn super well. Apologies. Oh dear. So if I were to recopy g, it would look something like this. So then if I were to draw the sum looks like it would start at the origin, kind of go out to this position here. And this would be the sum of r plus g. Which we can see that geometrically, now let's do it using the way we just talked about, where we can add the components. So in this case, I would say the sum is the sum of 2 comma 1 plus 1/2 comma negative 1. So I just add the x component, so 2 plus 1/2. And then for y, I get 1 minus 1. I add the y components. So in that case, it looks like I get 2 plus 1/2, so 5/2. 1 minus 1, 0. Indeed, the sum is a vector that points 5/2 in the horizontal direction and doesn't point at all in the vertical direction. So this is a horizontal vector. Components just add individually. If you're subtracting two vectors, you subtract the components individually. Which that's nice, or at least straightforward. Let's see. Now, hopefully you like the Pythagorean triangles, hopefully you also like SOHCAHTOA, because now let's think about how we might get, so we've seen how given components, you can get the magnitude. And we saw that using the Pythagorean theorem. Given the magnitude and direction, how might we get the components? So now, how can we go the other way? If I tell you, e.g., that I have some vector with a length equal to 3 meters, and it points 30 degrees above the x-axis. What is Rx and Ry? What are the individual components of the vector given I know how long the vector is and kind of what angle it makes with respect to my coordinate system? So let me lay down my coordinate system. Here's x, here's y. And maybe the vector is something like this. Maybe this is r. Okay. And again, what is this saying? This is saying that this angle here, it's making an angle of 30 degrees, positive 30 degrees with respect to the positive x-axis. I should have said this above, the positive x-axis. And so now the question is then, given that, what is this length here, which is r sub x? And what is this length here, which is r sub y? Really? This is a first for this to not work at my office. One day technology will just work. Today is not that day. Alrighty, very good. So now how can I get the individual components of this vector given that I know the length of the vector and the angle it makes with respect to one of the axes? Now, it might be a little bit hard to see, but we again have a triangle situation going on here. So I'm going to recopy that so we can make a little bit more sense of it over here. Where I know this angle, I know the length of the hypotenuse, I know that the entire vector itself is 3 meters, but now the question is, what is this component and what is this y component? And given that this is a right triangle and we know one of the angles, SOHCAHTOA to the rescue. So in this case, for example, I would say that the sine of this angle is equal to the opposite side of the triangle divided by the hypotenuse of the triangle, which in this case is the y component and the horizontal component. So I might say through algebra that r sub y in this case is the hypotenuse, or the length of the triangle, or the length of the vector, times the sine of that particular angle. Cosine is similar, though with the adjacent side of the triangle. So I might say that the x component here is the hypotenuse times the cosine of that angle. So again, given the triangle that I drew above, this is an example of how you can find the components of the vector. And I'm going to not only highlight those equations, but I'm going to also highlight it in reference to the particular triangle that's being drawn here. Just because adjacents and opposites depend on where the angle is being drawn, which angle you're identifying. So, I think this is actually how your book writes it. I actually don't like necessarily associating it with x and y. Really it depends on the problem. It depends on which side is the adjacent side and which side is the opposite side when we are doing these calculations. So for example, in the case of this problem, I would say that the horizontal component is 3 meters times cosine of 30 degrees, which is square root of 3 over 2. And then that has overall meters, and then the vertical component is 3 meters times sine of 30, which is a half. So this might be 3/2 of a meter, for example. And the x component is some irrational number. And again, kind of why I don't always necessarily like associating x's, because I feel like the fear here is you might look at this and think, oh, the x direction is always cosine, the y direction is always sine. And that would be potentially risky, because I could have drawn something, and we will actually see this when we do, say, boxes sliding down inclined planes, where if you have some inclined plane that's at an angle, I could draw this as my coordinate system, x and y, and maybe I have some vector here, b, that is being drawn relative to these axes, which are themselves kind of slanted. Then also, it could be that maybe I define that as my angle. So then my triangle looks something like this. This is theta, this is the hypotenuse, or the length of b, and then this might be the x component, and this is the y component, according to the axes that I drew down. But in that case, I would say, for example, the y component is the length of the vector times cosine. Because where I drew that angle is touching the adjacent side of that triangle is b sub y. So since cosine is adjacent divided by hypotenuse, then it becomes cosine is b sub y divided by the magnitude of b. So just again, math is a tool to an end in this class. You have to think about what you're doing in terms of the physical problem, which is why I'm trying to emphasize, throw down coordinate systems, draw which ways are the positive directions, so it is clear to you kind of what the answer has to be. And then also with the coordinate systems, you can adjust your answer to have either a plus or a minus sign depending on what the coordinate system is. I think your book defines it where it always uses the positive x direction, so that if you go beyond 90 degrees, the cosine, the sine will automatically have the correct sign, either plus or minus. But really what they're doing is they're making a choice by saying that you are always measuring angles from one of the positive coordinate directions, in that case the x-coordinate direction. Where I much prefer to kind of look at a problem by eye, and I can see, for example, like what I've drawn right here. I can see where the positive direction is, and so I know by looking at that vector b that I can throw down some triangles, and if I know the angles, I can use SOHCAHTOA and get the answer. And I know that at the end of the day, I just need to either manually or it will naturally occur that both the y and the x component must be positive, given the positive axes that are being drawn here. Okay. Let me elaborate just so that we know what these words are. So these IJK engineering notations, you can think of them as vectors, and particularly they're called unit vectors. What is a unit vector? A unit vector is a vector with a magnitude equal to 1. It has unit length. And what's nice about the IJK vectors is you can actually write down what the components are. You can think of I as just 1, 0. It points in the x direction, but not in the y direction. J is 0, 1, for example. And if I had a third dimension, then it would have been 1, 0, 0 for I, 0, 1, 0 for j, and then 0, 0, 1 for k. And you can convince yourself that the magnitude of each of these is indeed unity. It's just 1 squared plus 0 squared, all in the square root, which is indeed 1. So it's nice because they're essentially telling you the unit vector notation is nice because the unit vector is telling you the direction, and then whatever number is out front. So for example, if I said 3i, if I said r equals 3i, that's saying r is a vector that, since I is a unit vector, that says r has length 3 and points in the x direction. G being negative 9.8 times j says g is a vector that has length 9.8 and points in the negative y direction, because j is telling you it's in the y direction, but there's that negative sign. And then there can be unit vectors that are not simple ones and zeros. For example, 1 over the square root of 2, 1 over the square root of 2. You can convince yourself that this is a vector that points kind of diagonally at a 45-degree angle. But you can convince yourself by calculating the magnitude that it also has a magnitude of 1. So the idea here, and what's going to end up being helpful in this class, is with this sort of notation, either the IJK notation or using the coordinates, where you can break it up into how much is in the x direction versus how much is in the y direction, is when we learn how to do multiple dimensional motion, we're able to treat each dimension independently of one another. And it can become useful to understand kind of motion by breaking it up. If you have some general motion, like, for example, perhaps you have a ball rolling down a ramp. You may think that the coordinate system that makes sense is that you might make a coordinate system that has, say, the x direction and the y direction. And then you can figure out the position of the ball as a function of time in both the x and the y direction. And that would, there'd be some sines and cosines and whatnot flying around because of the inclined plane, but that would be doable. Alternatively, you might think that another coordinate system to do might be a coordinate system where one direction goes along the plane. Maybe I'll call that the A direction. And then the other direction of the plane is perpendicular to the plane. Call that the B direction. And then you could take the same motion and try to understand it in terms of components that lie along A and lie along B. In this case, it's nice because if the ball is always touching the plane as it rolls down, the ball only has an A component. It never has a B component. A B component would mean it's leaving the surface of the incline of the ramp. So as long as the ball is not flying off the ramp, using what I've drawn in red, that you would turn this problem into a one-dimensional problem. Just the one dimension would be either up or down the ramp. So that can be helpful in that regard. It also can be helpful, again, why is it worth doing the sort of projection coordinate system stuff? Intuitively, it can help us get a sense for how much, say, a force or an acceleration is causing motion, for example. Let me see. I think I can actually try to do it as a little demo. So here's, for example, is a coordinate system where I have some vector r that is not going to change. It's always going to stay the same shape, and it has some length or magnitude as such. If I put the vector at the origin and say have it point up at a fairly steep angle, I again can ask myself how much of this vector is pointing in the vertical direction compared to how much is pointing in the horizontal direction. So if I draw it from the center of the arrow, or I'll do it from the tip. If I do it from the tip, then in this case, this is the x component, and this is the y component. For that particular vector that is at some angle, and maybe I'll call it theta 1, for example. As opposed to if I take the same vector, I'm not changing anything about this arrow, it's still the same length. But now I'm going to point it, I'm actually going to get rid of this. But now I point it, say, at this particular angle. Same vector, same length, but now it's pointing in a slightly different direction. And then you can convince yourself that in this case, now the x component has become much larger at the cost of the y component becoming much smaller. It is pointing now more in the x direction when it's at this angle compared to when it was at its original angle where it was pointing more vertically. So this is a larger number than this. But in this case, this is a larger number than this. And you might think, who cares? This all seems like math. But where that can be important, at least for our intuition, is if we want to think of, say, a ball rolling down a ramp. I could have the case of a very shallow ramp, and then I could have the case of a very steep ramp. And there's a ball rolling down each. So the ball is ultimately going to have some motion that goes down both of those ramps. But if I wanted to ask myself, how fast do I expect the ball to be accelerating down the ramp? The question here is asking, essentially, how effective is gravity at pulling the ball down the ramp? You've experienced this if you've rolled the ball down a very shallow ramp, the ball takes a very long time to get to the bottom. Versus if it's a very steep ramp, the ball starts to drop almost immediately. Right, so knowing that gravity always points downward, I might use an arrow to represent gravity in this case, where maybe, perhaps, actually since my ramp is black, I'll use red. Right, so maybe if this represents gravity, it has some length, which might be 9.8 meters per second squared. If I put it here, the ball cannot go through the ramp, but it can go down the ramp. So what might be effective here is to have my coordinate system be a coordinate system that goes along the ramp and then a coordinate system that goes perpendicular to the ramp. So in this case, I can ask how much does the gravity vector point along the ramp versus into the ramp? And so in this case, this arrow right here corresponds to, say, G ramp, where this value right here might be G into the ramp. I'll just say G into. And since the ball cannot sink into the ramp, it is this component of the gravity that will matter to determine how fast the ball is accelerating. In contrast with this guy, where gravity still points down, the same vector, same length. But now let me ask myself, how much is this vector pointing down the ramp compared to into the ramp? So then I can again put my coordinate system down, and I'll choose one that is along the ramp and into the ramp. But now, the component that is pointing G ramp along the ramp is much larger in comparison to what it was before. And then the part that's going into the ramp is G into, is much smaller. So given that this length is longer than this length, as a result, this ball will feel more of a gravitational pull, or because the ramp will hinder the ball from just falling much less in this case than compared to this case. So thinking about how the vectors can be resolved into different coordinates is going to be very effective when we get into multiple dimensions. All right. I thought I would end, what time am I at? Okay. I thought I would end by just doing a couple questions from the book. So let's see, question 4 from chapter 3 of the questions, not the problems. So on page 56 for me. Two vectors A and B are commutative when you add them together. Is subtraction also commutative? So that's asking, is this true for two vectors? We could answer this geometrically. We could also answer this using the components that we just came up with. Now, if we wanted to disprove this, we would just have to find one counterexample. So let's say I have some vector A, and then I have some vector B, and I'll just keep them nice and simple. One's horizontal, one's vertical. If I wanted to do A minus B, that means geometrically I first go out in A, and then I go in the direction of minus B, so it would be going down instead of up. And then this vector here is A minus B. Alternatively, if I want to do B minus A, I would first go up B, and then I would go in the direction of minus A. So I would go out like this. And the ultimate vector looks like this. Those two vectors are clearly, the vectors in red are clearly not the same vector. So subtraction is not commutative. Perhaps not too surprising, since I emphasize that vector addition and subtraction obey very similar to numbers. I could also do it by components. Suppose A is some horizontal vector equal to 3, 0, and B is some vertical vector, maybe it's 0, 1. And you should get in the habit of being able to see this and be like, yes, A is purely horizontal, B is purely vertical. A minus B means I take the x components and I do the x component of A minus the x component of B. So that's 3 minus 0. And then I do 0 minus 1. So A minus B might look something like that. B minus A, I'll let you convince yourself, is instead that. So again, they are not equal. Turns out they're the same thing, just flipped, similar to regular subtraction. 3 minus 2 is the negative of 2 minus 3. All right. How about problem 1? What is the x component and the y component of a vector in the xy plane if its direction is 250 degrees counterclockwise from the positive direction of the x-axis and has a magnitude of 7.3 meters? So write down, what do we know? We know the magnitude is 7.3 meters. We know the angle is 250 degrees, measured from the positive x-axis. And the question is, what is the individual components of this vector? So if I define my axes to be kind of the classic ones, it's saying I go out 250 degrees, which is about here, and then I draw a vector, and that's r, that has some length equal to 7.3. And the question now is, what is r sub y, and what is r sub x? Now, if you use the book notation, then, like what we wrote down before, these will hold, and if you use 250 degrees, this will get you something like negative 2.5 meters, and this will give you something that's 6.86 meters. And you should always interpret that, does that make sense? If I look at that vector I drew in red, it's pointing to the left and down. Left is the negative direction for x, and down is the negative direction for y, so I should expect both of these numbers to be negative, which they are. So that's good. Alternatively, I could have thought something like, well, if this is the vector, I could also say, if that other angle is 250 degrees, then this angle is 30 degrees. But then I have to be careful what I'm measuring, because then I would say that the y component is r cosine of 30 degrees, and I have to manually throw in the negative sign in this case, because I know the answer must be negative, but r cosine 30 is not going to be negative. But given this coordinate system, I can manually pop on the negative sign. And Rx is then again negative r sine of 30. And you will get the same answers. You might think, well, these equations look quite different, but remember this theta here, this is a different theta, that's 250 degrees as opposed to 30 degrees. But you get the same answers at the end. How about problem 9? Here, I'll do 2 more. two vectors are given by blah, and find their sum, find their difference, and find a third vector such that a minus b plus c equals 0. Okay. So this is being written in 3 dimensions. So I could write this as, say, I'm going to be sloppy and not track the units. You know, A might be written something like this. B might be written something like -1, 1, 4, -1, 1, 4. If I wanted to do it as columns, your book writes it using IJK. Actually, it asks to use unit vector notation, so I should have used IJK, but it's okay. You can see this done in multiple ways. And then the question is, what is A plus B? A plus B in this case is I take the two x values, 4 and -1, I add them together. That gives me 3. I take the two y components, I add them together. That gives me -2. I take the two z components, I add them together. That gives me 5. What about their difference? Same idea, but I subtract b rather than add b. So instead of 4 minus 1, it's 4 plus 1. It's -3 minus 1, and then it's 1 minus 4 in that case. And then it's saying find some third vector such that when you add all 3 of these vectors together, you get the null vector, or you get 0. They did not write a little arrow over the 0. Test. So C is unknown. So I could just write this as it has an x component, it has a y component, it has a z component. Our goal now is to find these 3 numbers. If I want to add them together to get 0, again, I can look at the x components, 4 minus 1 plus cx, the y components, -3 plus 1 plus cy, and the z components, 1 plus 4 plus cz. And I want this to equal the null vector, which is a 0, 0, 0. So again, that suggests 4 minus 1 plus cx equals 0, or that cx equals -3. That suggests -3 plus 1 plus cy equals 0. That suggests that cy equals 2. 1 plus 4 plus cz equals 0. That suggests cz equals -5. It's nice because the algebra of each dimension can operate independent of each other. Oh, sorry. They wanted a minus b plus c equals 0. Well, I will let you try that on your own. Let's see, are we done? I think this is, I have in my notes 28-ish. So I think this is a problem I made up, but might be close to 28. Suppose there are 2 people that take a walk. The first person takes a walk by first walking 3 miles due east, and then walks another 4 miles to the northeast in such a way that they are making a positive 30-degree angle from the east direction. And they walked 4 miles. Now a second person takes a walk, and they start by walking 2 miles to the northwest, such that the angle they walk is about 10 degrees north of west. And the question is, what do they have to do for the second leg of their journey such that they both end up at the same spot at the end? And find what that vector is. All right, so I might start by giving some notation. So I might say the vector A is a vector that is 3 miles east, where I'm defining a coordinate system where east is positive, west is negative, north is positive, and south is negative, with my arrows representing which directions are positive, which are negative. B I might then represent as a vector that's 4 miles long and 30 degrees northeast, or north of east. C is a vector that is 2 miles long, 10 degrees north of west. And then D is to be found. And let's try to find the components of this fourth vector D. And then you can look in the book that if you have the components, we've seen how to find the magnitude. And then it's just another SOHCAHTOA to get the angle. In that case, you're using the tangent of to get the angle. Or really the arctangent. So if I were to approach this, I would first try to get this into notation that I can use. So A being 3 miles to the east, that would be a vector that is 3, 0, if in units of miles. East is positive, so it's positive 3. B is then, you can resolve it into components. This would be, I guess, 4 cosine of 30 and 4 sine of 30. And again, where is that coming from? I have my north and my east, and then it looks like I drew B as something like this, where this is 30. And again, you have your kind of good old right triangle here, where you know the hypotenuse is length B, which it tells you is 4 miles. Given that and the angle, you can find the individual components. So did I write down, so it looks like, well, sine of 30 is a half. So then this is, I have 3.46 miles and then 2 miles. All right, then what about C? C, I know, is pointing to the left and up, so I should expect the first number to be negative and the second number to be positive. And given where the 10 degrees are, I could evaluate that as 2 times cosine of 10 degrees, but I have to manually put in the minus sign because I want it to point to the left. And then this is then 2 sine of 10 degrees, which will be positive. Itself will point straight up, which is appropriate for that vector. So then this is negative 1.97, comma 0.35. And again, kind of going back to what we did at the board, that angle is very slight. The vector C is essentially horizontal. So it makes sense that the horizontal component is much bigger compared to the vertical component. It's doing most of its moving in the horizontal direction. And so what is the relationship? If they start at the same place and end up at the same place, that means if I were to do the vector sum A plus B, that must then equal the same vector sum C plus D. If I take C and draw out that vector, and then I draw this D vector by putting point to tip, that ends up at some point. And the idea is that A plus B ends up at that same point. So then I could say the vector D is A plus B minus C as vectors. And we've seen how to do that. You do it component by component. I get something like 8.43 miles, comma 1.65 miles. Which, if I look just at the picture I drew, that kind of jives with what I've drawn there. Because horizontally, they have to make up for the 3 miles, the 3.46 miles, and the 1.97 miles in order to end up at the same positive x-coordinate. And then they've already been moving vertically or towards the north, so they don't have to go quite as far north in this last leg of their journey to match the same location as the first walker or jogger. All right. We are done with vector arithmetic. So now we will start using this to understand multiple dimensional motion.